Okay, so welcome back for the second talk of the morning. And it's our pleasure to have Cristina Anghel telling us about universal link invariant via configuration spaces.
So thank you very much. First of all, I would like to thank you for the invitation. It's a pleasure to be here. And yes, so my aim is today is to talk about some link invariants which come from representation theory. And my aim is to study them from a topological point of view. So my goal of the talk will be to describe the topology of asymptotics of such invariants using configuration spaces. And so having this goal in mind, I will structure my talk into three main parts. So I'll start with the motivation. Then I will talk a bit about the representation theory, which is behind quantum invariants, and how they were defined from that perspective. And then I will present which are our topological tools in order to arrive at this topology of the computation space. So I'll start with my motivation. So quantum invariants originally come from representation theory. And in this case, the invariants that I'll talk about are colored polynomials and colored Alexander polynomials. So here, if we note at the level of link invariance, the invariants that I will be talking about will be sequences of invariants which are indexed by natural numbers. So more precisely, if I fix a natural number n, we have two sequences of invariants, namely the colored Jones polynomial and on the other side, the colored Alexander polynomial. Which often is called ADO polynomial. So this is at the level of link invariants, and the way that they originally were defined comes from representation theory. And now, also the representation theory gives us sequences of higher level invariants, namely quantum invariants for three manifolds, which means that I can build up three manifold invariants using this kind of quantum invariants for underlying links which describe three manifolds. And mainly here, what we have are the Wittgenstein derived invariants. And on the other side, we have Constantino-Kirpatov invariants. So somehow all what we have from this representation theory is that we have two sequences of quantum invariants, color-Jones polynomials and colored-Alexander polynomials on the semi-simple and non-semi-simple side. And somehow they are building blocks for three manifold invariants, semi-simple and non-semi-simple. And somehow the important thing is that in order to build up the three manifold invariants, we need the quantum invariants for links. So not just about for knots, but really for the links. And my motivation is somehow the geometry which is behind its invariants. So there are various conjectures due to Witten and then the Kashaev and Murakami, which predict that asymptotics of these invariants contain geometrical information. So here we have a question, which is what is the conjectural geometry which is behind all these invariants? And somehow motivated from this conjectural geometry, what I would like to see is to try to understand these invariants from topological perspectives. So here I would like to use topological tools. So somehow at the level of topological tools, what I mean is trying to understand these invariants as intersections, graded intersections of certain Lagrangian manifolds in configuration spaces. So I will zoom out and then tell you exactly which are the configuration spaces that I'll be using and so on, but somehow as big picture, this is what we should have in mind. And this is what I will mention as being a topological model for an invariant, a graded intersection. So for the first case, namely here for the Jones polynomial, the first topological model was done by Bigelow and Lawrence. And then there are some other people which worked on representations of braid groups and homological representations. And here I should mention Ito, Kono, and Martel. And one result which I would like to mention is that 2 years ago I showed that, 1 year ago, we can see these two invariants from the same perspective. So in unified, I show a unified topological model. And from this unified topological model, we are able to understand both invariants at a fixed level from the same configuration space. Now, my aim for today, so my motivation is the fact that somehow it's conjectured that this would also contain a lot of geometry, asymptotically. So what I will be talking today is what happens when you really see the asymptotics. So at the asymptotic level, Habiro defined an invariant which unifies all color-Jones polynomials in one single quantity, which he calls the universal invariant. So this is an invariant which unifies in a formal power series all these invariants. But the way that he did it, somehow it works just for the context of knots. Now, for the links case, it remained open, and also what happens on the non-semi-simple side, both for knots and for links, that's also open. Okay, so links. So my aim for today is to provide a positive answer to this question, which originally comes from representation theory, providing universal invariants using topological tools. So here my aim is to show a universal Jones and ideal link invariance. And these two universal invariants will unify all Jones polynomials on one side for links, and all four Alexander polynomials for links on the other side. Okay, so now I'll state the result, and then I'll zoom in to show which are the tools for the construction. So we'll have two results which somehow will go in parallel. The first result will be a universal ideal invariant. So what we'll do is to construct an invariant, which I'll be calling gamma A of a leaf. And this will live in a certain ring, which will be a completion of a polynomial ring. I'll talk about this later, which I will denote FH has. Such that this invariant unifies all ideal invariant for leaf.
Does A stand for your last name?
Sorry?
So what does A stay for?
A, it's ideal.
Say again?
A, it stands for the ideal.
Okay.
Because we'll have a parallel one, which is for Jones. That would be J.
Okay.
Just to somehow remember match the invariant. Okay. And then secondly, so this will be a universal Jones invariant. So what we'll do is to define gamma J of L in another completion of a polynomial ring, which will be denoted by Lj, such that it globalizes all Colorado polynomials for links. In a geometric way. Okay, so my aim for today is to show you somehow a bit of the idea of constructing the rings, and then a bit of the idea of constructing the events in those respective rings. The idea of constructing the rings, that's purely algebraic, and then the way of constructing this invariants is geometric using computation space. Okay. So now I'll start the first part of the talk, which is related to the representation theory, which is behind this. So first I'll talk about quantum invariance. So the quantum invariance that I will be talking about originate in the representation theory of the quantum group UPSL2. Okay, so that is the starting point. And somehow this representation theory is very interesting with respect to the variable Q. So if you take Q generic, you get one theory, and if you take Q root of unity, you get a different theory. More precisely, if Q is generic, then somehow you get something each time when you fix an L component tuple of numbers, M into the power L. So for me, L, little n will be always the number of components of the link. Okay? And now if I fix an n tuple of natural numbers, then the construction due to Rashid and Turaiv, which was done in the 90s, provide us a link invariant, which is respect to this multi-level M. And that's a Kohlrausch polynomial at level M. Jn of L. And what I want to mention is that this invariant is always an invariant in one variable, regardless of the fact that we have one component or more components. So it's a Laurent polynomial in one variable, and then the ring that it belongs to, I will denote it by gamma mj. Even if it's always the same ring, it's a Laurent polynomial ring in one variable. And now I would like to make a parallel with what happens with Q root of unity. So if you put Q root of unity, so if you take the primitive 2m root of unity, and I'll denote it by psi m for the next part, then the representation theory changes, and then we have an invariant in L variables. Okay, and that is the construction due to Akutsu, Debuki, and Otsuki, which was after the Rashid-Turaiv construction. It's a modified version of the Rashid-Turaiv, and that provides an invariant, which is the polar standard invariant of the link. And this time we'll get L variables. And this invariant will live in a more complicated ring, which I denote gamma m, lambda m a, which has this form. Okay, so what I want to say is that somehow the difference between these constructions is that if I fix a link, the semi-simple construction always gives me a polynomial in one variable, but it's indexed by tuples of L components. On the other hand, the non-semi-simple invariant gives me always an invariant, but in one variable. So here I have extra information. And the ring in this case is more complicated than the initial ring.
And so, sorry, how should we interpret these extra variables, and also what's the last line?
So I take the inverse of this. So I take the ideal geometry by this, and then I invert it.
Okay. And is there a way that we can think of these, like what are these variables associated?
Are the weights. So each variables is a weight. So you look at the representation here of at root of unity, and xi should be the root of unity xi to the power.
I see. So
people sometimes you parameterize by lambda.
Yeah.
Which is lambda 1 up to lambda L, and then here x is lambda I. Sorry, xi I. Xi n to power lambda I. So somehow you can either think that you parameterize it by complex numbers, or you can repackage it all this quantity in one variable. And this is the way that I prefer to think about it.
Okay. Yeah, so somehow the x is the n for the jumps. Yeah.
Exactly, yeah. So this is why I have to invert this system. Yeah.
Oh. But anyway, so it's you have to specify x as the roots of unity, right?
X are the complex variables. My root of unity is this xi. That's a root of unity, and then somehow the representation is here, it's indexed by complex numbers. So for each complex number, I have a representation, and then the idea is that I can repackage all the theory so that I obtain a polynomial with that kind of coefficient. So this is like I can obtain a polynomial in xi rather than a complex number, and I prefer to see it in this way. Some people are just working with the lambdas, which are complex numbers, but it can be repackaged in this way, and then it's the same information overall.
So, so is it the same invariant you were talking on the kind of upper part?
Yes, of course. Yeah.
And the
Yeah. So Jm, it's exactly the Color-Jones polynomial. And then here, psi m is a Color-Alexander polynomial.
Yeah.
At the beginning, I didn't enter into the details that n it's for the Color-Jones case. Here we have L components.
Okay.
But now I have to be more precise. So yeah. Okay. Now, and so this is what happens on the representation theory side, and now I'd like to say which is our strategy to build our universal invariants. On the topological side. So our strategy somehow will be split into two levels. So our input is an L component link. Which is oriented. And we'll be looking at it as being the closure of a braid with n strands. Okay, we can always do that. And so what will now we have two steps. The first step is topological, and the second step is algebraic. On the topological side, we'll fix a level n, and once we have the level and the number of strands of the braid, we'll look at the one particular configuration space. So we'll look at the configuration space of n-1 times n-1 plus 2 particles in the puncture disk. Okay, so the puncture disk is the puncture disk which I've drawn here. So if you count, you can see that I've drawn exactly 10 plus 2 punctures. And I will be looking at the configuration space of that image. And now in this configuration space, we'll define a graded Lagrangian intersection. which I will denote by gamma n, which will depend on beta, and it will belong to a polynomial ring. And somehow this Lagrangian intersection will be basically a graded intersection between Lagrangian manifolds. And the Lagrangian manifolds, I will zoom into the details later, but somehow will be supported on this kind of pictures. Okay, so this is a configuration space that you should have in mind, and these are the submanifolds we should have in mind. And I will say the details in the last part of the talk of that. But now what I want to say is that somehow this is the topological part of the construction. And once we do this part of the topological part of the construction, the next part is algebraic. Because so far, what we did is it's at a fixed level. As I mentioned, I'm interested in the asymptotics, which means that I'm interested to let n vary and tend to the infinity. And so for the second part, that will be algebraic, and we will use quotient rings.
Maybe just a piece for the Alexander, the configuration would be different.
Sorry?
For the other one, for the Alexander, the color Alexander, the configuration space would be different.
No, so for both of them, so this will be the same for both of them.
Okay.
And then in the second step, we'll distinguish the two cases.
Okay.
Okay, yeah, thank you. That's a very good question. So now at the level of quotient rings, we'll make the difference between the two. So the idea is to start from this ring and construct new rings. And from this quantity, to take quotients and then look into these quotient rings. So we'll construct the first quotient ring will be denoted by L and J. And the second quotient ring will be denoted by L and H. Okay. And somehow I'll take this invariant and then look in these quotients. And I will obtain gamma mj and gamma na. And somehow the first theorem will be that these are new link invariants. So somehow opposite to gamma n, which depends on the choice of the braid. These are really invariants of the ring. And now the second part concerns, so this is still at fixed level. And now I will put the level to tend to infinity. So what I will do is to consider a projective limit of this ring. And the theorem will be that I can consider a projective limit of these rings. And in parallel, I can consider a projective limit of these elements, and I can unify them in a single quantity. So this will give me gamma G of L and gamma J of L in Lj. Okay, so that's my strategy for the proof. And now I want to continue with somehow zooming in on this procedure. So what is somehow the general philosophy of constructing a universal invariant, which unifies a sequence of given invariants? Okay. Maybe. With what can I read? Is this one?
Oh,
This one. Ah. Yeah, maybe it's better. So that is the second part concerning the universality procedure. So basically, this philosophy of obtaining universal invariants somehow will be, so I make a parallel with what happened in Aubière's case and what happens in our case. And actually, both situations can be put into the same general philosophy, but with different algebraic tools. So the general philosophy is that, let's say that we start with a sequence of invariants. Which are denoted by Jn. For example, we can have in mind Kohlrausch polynomials or ADO invariants. But the idea is that we fix a sequence, and then the idea is that each invariant lives in a ring. Okay. Let's say Rn. Okay. And then these rings can vary as you vary n. It wasn't the case for Kohlrausch polynomials, but it's the case for Kohlrausch-Alexander polynomials, for example. Okay, and the question is, how can you repackage them in a single quantity such that from that single quantity you can read them off, all of them, if you make specialization of variables. And the first idea is to enrich the rings. And by enriching the rings, I mean to add variables. So the first step is adding variables. And specialization maps. And so that I can enrich this ring R to a ring R and hat. That specialized to the, and I have a specialization map from the head version to the non-head version. And now the second part is to, so I have to do this in a coherent way such that I can take a limit. And the second part is to go to the limit and consider the projective limit of these rings over all n, such that they give me a limit ring. And now, if I obtain a limit ring, the second part of the construction is to provide a link invariant in this limit ring. Okay, so that's part B. Define a universal invariant. Which are denoted by I of L. And this IOL will belong to this limit ring, such that I can go from, so using the specialization maps, I can go to the limit and I'll have specialization map from the limit to each of my rings. And the idea is that this universal invariant recovers any level of invariant by the specialization map. Okay, so in this sense, I managed to globalize all the invariants in one single quantity. Okay, and now I'd like to say a parallel. So what happens in Habirov's case and what happens in our case? So having in mind this general philosophy and knowing that we want to unify Color-Jones and Color-Alexander polynomials. So on the algebraic side, we have to be careful which are the rings that they belong to and how to enrich the rings such that we can unify them. So for Color-Jones and Color-Alexander polynomial, I would like to remind you that the rings are this gamma J and gamma A. And so what we will do next is to enrich these two rings simultaneously. So what I'm going to do is to consider this Ln to be the normal polynomial ring in these variables. So here, when I put a bar, I should say that each time when I put a bar, I have L components. Because when I work with a ring, the ADO polynomial case obtains a polynomial in L variables. Okay, so this is my way of encoding it. Okay, and then so I consider Ln to be this non-polynomial ring in these variables, and then not known in W's. And then I consider specialization maps from this ring Ln to the ring where I have the M's Color-Jones polynomial, and to the ring where I have the M's ADO. Okay. So this will be maps which I will use later, but somehow just to have in mind, they're related to this procedure of enriching the ring and then making the specialization. And now I'd like to see what is a parallel between what happens in Habirov's case and what happens in our case. So Habirov's algebraic universal invariant that's on one side, and here I'd like to mention where we are going. So in his case, so here let's say that we look at the sequence of Color-Jones polynomials for knots, which are polynomials in one variable. Okay. So if I look at this sequence of polynomials in the variable d, so basically what he did is to add a variable x. So as a parallel to the first part of the construction, he added x and constructed an invariant, a formal power series G of k, x, and d in a ring such that this university invariant recovers the color Jones polynomial at level n if you specialize x v d to 1 minus n. Okay, so this is exactly the philosophy of going to the limit and then specializing it at the level n. And now I would like to one point that I would like to say is that somehow his construction is directly at the limit. So directly at the limit ring, and then from the limit he reads off the nth level. Now what we'll do, we'll have at the end we'll provide the inverse invariant, but it will have a different method of construction. So here we look at the sequence of colored Alexander polynomials, J2 of L and X bar and so on. And our construction will be done in 2 steps. The first step is to fix an n and then define. So for us, on the algebraic side, we will add variables. But since we are working with links, we have to add more variables than in Habiro's case. Habiro had always polynomials in one variable. Here we have polynomials in L variables. So we will add 2 types of variables, which are W, U, X, and D. Sorry, Y and D. And using these variables, we'll construct quotient rings. And then the idea is to construct for each n to provide gamma hat n in the ring at level n. And this will be a link invariant. Defined in a fixed contribution space. And the theorem will be that this link invariant contains all what happens with your invariants, ABO invariants, up to level n. So it unifies all the non-semi-simple invariants up to this level. And then the next procedure will be to go to the limit. So from this, we consider the projective limit, and we construct our gamma hat. So this part is projective limit over n. But as a parallel, what I would like to say is that in this case, Habiro constructed something directly at the limit, and directly from the limit, you read off the nth component. Whereas here, the strategy is to unify more and more colored Alexander polynomials and then let the color tend to the limit. Let the color tend to infinity. Okay. And so now I would like to finish the last part of the talk, somehow zooming in on the geometry that is needed to define this link invariant in a fixed configuration space.
And the second method also work for the Jones?
Yes, yeah. So in the end, we'll obtain the same thing will work for Jones. Yeah.
But like the one of Aubière cannot be generalized for the color Alexander. It's hard to understand.
So Habiro set up the Habiro did just for, so that works just for knots and for Jones, for the color Jones polynomials. And then what we do is to do it for links. And our method works for both.
Mhm.
So both for Cordjon's and Cord-Alexander inversion. Okay. So yeah, I'd like to go and zoom in on the geometrical side. So that is somehow the third part. Which are our topological tools. So we fix n. And then see the closure of beta. And then, so as I mentioned, we will use the configuration space of little n minus 1 times big N minus 1 points. Plus 2 in the puncture disk. And then on this configuration space, we will plug in a local system. So this local system will be an LN local system. So I just want to remind you that Ln is a Laurent polynomial ring in 5 type of variables. It's on the left hand side of the blackboard. Okay. And now I would like to draw a picture to somehow say which are the variables of this local system. Okay. So we have our puncture disk. And then I consider 2 n punctures.
This is an ordered configuration space, right?
Unordered configuration spaces. Yes. Yeah. So I consider that I have 2 n somehow principal punctures, and I add 2 special puncture, one in the middle, and one star puncture on the side. Okay, and now around the principal punctures, I will have my variables x. So the local system will count the monodromy around puncture I by the variable xi. And the monodromy around the symmetric puncture with the variable xi d2 n minus 1. N minus 1 first.
It's a rank 1 local system.
Sorry?
It's a rank 1.
It is one local system, yes, yeah. But what we like to emphasize is that this local system really depends on the level. So once we, this is because of the way that we count the monodromies around symmetric punctures. So once I increase the color, I count monodromies around symmetric points with different monodromies, which is multiplied by this. And somehow this, in some sense, this D is the variable of the Cordjon's polynomial. Okay. And I have also some other kind of variables. The variable y is the monodromy around this special puncture. And the variable d comes from the fact that I work in the configuration space. Namely, if I have 2 particles and I swap one with the other, since I'm unordered, this swap will be counted by the variable d. So for people who do symplectic geometry, that can be seen as the intersection with the diagonal of the symmetric power. If I don't work in the configuration space, if I allow multiplicities, I have a twist around the diagonal of the geometric power, and that's a variable D. So overall, what I want to say is that in this Ln, I have 5 types of variables. And from my picture, you can see that x, d, and y are really geometrical. They are monodromies. And then somehow this w and y, there's something extra which I will add because of the nodes in symbol part of the story. And I'll say that these are quantum weights. Which you do not see it in the geometry of the local system, but you will see in the way of describing the intersection form. Okay. So I consider this local system, and then the idea is that once I have the configuration space and a local system, I have a graded intersection, which comes from it. And this is what I will use. I'll use the graded intersection associated to this phi n.
I'm a little bit confused because I would expect just, lowercase n points, relation of lowercase n points. Why you get that many points? N minus 1 times n minus 1 plus 2.
So you were expecting what? Conjunctions of?
I would expect just lowercase n points, right? Since it's a closure of a brain with n components. How you get
Yes, but I mean, you want quantum invariance. And once you have quantum invariance, you have the color. So this curly n, it comes from the color of the quantum invariance. And so that's the philosophy. Once you increase the color, you increase the number of particles in a way that depends on this n.
It's like using some cable.
Right,
Sorry?
It's some kind of cabling, right?
Yeah, I think you can see what it's like. I mean, I'm not using the cabling. I mean, the proof somehow makes the correspondence with the representation theory. But you can also think in this way. I mean, the cabling is reflecting in the fact that each time I add n variables. Okay. So once I have this setup, right, this setup is general. Somehow the tricky point is how you define this local system to have a well-defined intersection.
Can we erase this?
Which them?
This n is fixed once forever or
Little n is fixed once forever, so the disk is fixed. But now the configuration space changes with the level. So basically, what I do is to fix the puncture disk, and then each time when I increase the n, I increase the number of particles, and I increase the volume of the local system. Okay, so now I want to say which is my graded intersection, and for this I need Lagrange transform manifolds. So what we do is to define Lagrange transform manifolds. Which are indexed by some tuples. I bar, which has little n minus 1 components, which can vary between 0 and the color minus 1. So what I will do is for each I I will construct two submanifolds. So on the left, what I do, I look in the puncture disk, and I will construct a submanifold in this configuration space. And the way to do it, so I denote the submanifold by Fi. Fin. So the way to obtain this submanifold is to look in this puncture disk. I start from the boundary and I skip the first puncture, but I draw I1 parallel arcs towards the first puncture, towards the second puncture, sorry. Then I draw I2 and so on up to IN minus 1. Then to the middle puncture, I draw just one curve. This is why it's dotted, because it doesn't have multiplicities. And then what I will do is to complete symmetrically with respect to the color. So up to this one, I will draw n minus 1 minus in minus 1. And up to here, I will draw n minus 1 minus I1. And to the last puncture, I just draw one curve. So in some sense, the condition is that if I look at two symmetric points to the left and to the right, the total number of arcs that end in those points are exactly the color minus 1. Okay. And in this way, we can obtain the Lagrangian submanifold by taking the product of all of these curves, all of these arcs, and then make the quotient by addition of the symmetric group. So if you count carefully, you can see that you have exactly this number of arcs, n minus 1 times n minus 1 plus 2. And then by making the product and then taking the quotient, you obtain a submanifold in the configuration space. And that will be my submanifold F. And now dually, we'll construct a dual submanifold by taking the same puncture disk, but this time we will draw ovals. So I will draw ovals around symmetric punctures. The central one and the last one, I just take them as they are. And then on all the rest, I'll consider unordered configuration spaces of this number of particles. And now, if I take the product of all of these configuration spaces on all of these ovals, this will give me a second submanifold L. So N, I, N. And then in this way, I obtain two Lagrangian submanifolds in the configuration space. And what I like to say is that somehow all of this is intrinsic. So at the moment, I do not see the braid. But the way to see the braid is to use the fact that the braid group is the mapping class group of the puncture disk. So if I take my braid with n strands, I can consider beta tilde, which is beta, where I add a triple braid with n minus strands. And now what I can do is to act with this, so I have an action of this beta on the puncture disk. And now this action, this braid group action on the puncture disk, which basically means that you will rotate the punctures one around the other. This action will pass to the level of configuration space. And everything behaves well, and you obtain an action on this submanifold. So I can consider this beta tilde F. And I keep the second submanifold fixed. Okay. And with this setup, so basically I will build up my weighted intersection by considering all intersections. So there we have the previous intersection. Here we have the submanifolds. And what I will do is to consider the sum of all possible intersections between submanifolds, which is indexed by all possible choices of i's. Yeah. So the definition is so I consider my gamma n of beta. So I have a framing correction. And then what I do is to consider the sum over all i's from 0 to the color of another term, which depends on W. So here are the quantum weights which I'll add. And except of these terms which depend on the quantum weights, I intersect these submanifolds via my degree intersection. So I take intersect the F and then L. And I look at the gradient intersection and the volume. So this will give me an element of the ring element. Okay. And now, so this is purely geometric. And then as you see, it doesn't depend on this I mean, you can't see any semi-simple or semi-simple version here. This is purely geometric. And it provides this weighted Lagrange intersection in this ring. And now the theorem is that somehow this gamma n contains all Color-Jones polynomials and all Courte-Alexander polynomials through specialization of coefficients. So the key point which is the implication of Color-Jones and Courte-Alexander polynomials, says that the weight intersecting at level n contains all Color-Jones and LBO. At levels bounded by n. More precisely, if I want to obtain Jm of L and B, I can start from my gamma n, and then I can specialize through psi mg. And that is for any m which is bounded by m. And then if I want to obtain the colored Alexander at level M, I can start from the same gamma n, but this time I specialize through psi MA. That's for all M bounded by M.
What is the link invariant?
Sorry?
Is it the link invariant?
No, this is not a limit. So it's somehow which captures everything up to level M. And then in order to make the link invariant, we go to the quotient. We go to the quotient, we obtain link invariance. And the idea is that this link invariance will unify all colored polynomials up to level N and all colored Alexander polynomials up to level M, respectively. And then the procedure is that after that, we show that we can pass to the limit. And everything have a good assimilative behavior so that we have over defining. Okay, I think that was all what I wanted to say, so I think I will stop here.
Thank you. Any other question or comment?
I suppose probably the proof is somewhat complication. Like I assume you're relating it to some farming. Like basically, I guess my question is it computable this in area? Grade or something.
So the proof is somehow in some sense is theoretical because I make the connection with representation theory. Okay, so I know that somehow all what I construct there specializes to colored and colored Alexander, and then I use simplification with representation theory. Now I'm working with Roland Vardevin on a computer program to be able to read off everything from the art in action on the breadbook, art in action on the puncture disk, and then somehow from that we are working to make it computable directly on the disk model. So it's work in progress.
Cool. And so then I guess I was wondering, is this like an SL2 story? Is like, do you expect a similar thing to work, maybe different ones, or like the other groups, or?
That's a great question. I would like very much to make it work, but at the moment, it's related to the SL2 because somehow this action on the puncture disk is related to the representations of UKSL2. But I think it should be it should be a more general theory behind it, which probably should work for other quantum groups, but you should use different configuration spaces. I expect it should be something like colored configuration spaces or something like that. Yeah.
Maybe at the beginning, when you had your plan, you explained that something was done for link, but then from link we can go to three manifolds. So, like here, this universal invariant after link, but is it easy to go up to?
So yeah, thank you for this question. This is what I would like to do next.
Okay.
So I would like to. So it's work in progress. To upgrade this at the three manifold. So I'm planning to use this gamma n for links, and then to go and understand the Wittgenstein-Trev and Cristina Anghel rho from this perspective. So it's work in progress. Yeah.
No other question. Let's thank the speaker again. And for this year, the 6 seminars are over. So yeah, thank you all for coming and joining us.
Thank you for organizing it. Thank you.
I'm going to just people. I think yes. Yeah, it was fine. And now I don't know how to do this.